this lesson, we'll discuss the application of regression algorithm with R programming through a financial market case study. This includes modeling security price data with single and multiple features. First, we'll train the algorithm using the training dataset and examine various goodness of fit measures. And next, we'll test the algorithm on test dataset and examine its out-of-sample prediction efficacy. In this video, we'll introduce ABC stock price case study, which entails forecasting stock prices using regression algorithm. Please note that stock price prediction or stock return prediction is an attempt to determine the future value of a company based on analysis of factors which impact its price movement. There are a number of factors that help in predicting stock prices. These can be macroeconomic factors like state of country's economy, growth rate, inflation, and so on. There are also other factors that are more specific to a stock like profit margin, debt to equity ratio, sales, and so on. Let's examine the data provided in this case study. So we are given data for market prices of a company ABC along with Nifty and Sensex. These are market indices that represent broad market-wide movement of securities, and we are also given data of dividend announcement and a sentiment index. Let's discuss this data in more detail now. Think of a portfolio manager who has to build a model for a particular stock, which is ABC in this question and under consideration. The manager wants to predict the ABC stock price return for this stock using regression model. The data provided to us starts from 2000 and goes till 2019. So we have approximately 19 years of data. We can construct daily returns as provided here. So we have daily returns of ABC. These are provided in this column. And next, let's call it column B. Next, we have daily return on Sensex. This is column C, and daily return on Nifty in this column. Please note that Sensex and Nifty are Sensex and Nifty are two main stock indices used in India. They are the benchmark Indian stock market indices that represent the weighted average of the largest Indian companies. So Sensex represents average of 30 largest and most actively traded Indian companies. Similarly, Nifty represents a weighted average of 50 largest Indian companies. Another variable here is dividend announcement, which is provided here in this column. This variable attains a value of 1 if the company has announced a dividend on a particular date and 0 otherwise. So for example, if the value is 1 on this given date of 10 January 2000, because the company ABC announced a dividend on this date, and it is 0 for other days, as we can see, when the company did not announce any dividend. Please remember, this is a dummy variable. Lastly, we have sentiment variable in this column. It is a sentiment score that quantifies how investors feel about ABC company. It can be based upon news analysis or upon option market analysis or based on some survey of investors. We would not go into details of the construction of this score here and take it as given. A very high sentiment score represents bullish emotions of investors and vice versa. To summarize this video, in this video we introduced ABC case study problem with respect to stock price forecasting. We discussed the background of the case study, its relevance and implication for financial markets. We discussed the variables and data provided in the case study, the interpretation of each of the variable and its implication for the regression modeling. In this video, we'll introduce the problem statement with the ABC case study. The problem statement will be demonstrated and implemented with the R programming. In the first part of our problem implementation, we'll start with the simple linear regression model. We'll start the study with data visualization. We'll plot the returns and cumulative returns for ABC stock and market indices like Nifty and Sensex. Then we'll segregate the data into test and train dataset. We'll train and build the model using the simple linear regression algorithm, using market index as the independent variable and ABC returns as the dependent variable using the training dataset. So we'll train the model first. Then we'll evaluate the model with various goodness of fit measures and through visualization. Thus, we'll test the model, and also as a part of testing the model, we'll evaluate the out of sample model performance on test data set using various quantitative measures and also with visualization. In the next set of implementation, we'll employ multiple linear regression algorithm. We'll start with training and building the model using multiple linear regression algorithm, using market indices, sentiment, dividends, among other variables with the training data set. Next, we'll evaluate the model with various goodness of fit measures and through visualization. There are several issues that we'll deal with. These include multicollinearity, heteroscedasticity, and autocorrelation. We'll examine these issues and we'll try to find ways to resolve them. We'll answer the question how to resolve these issues in the estimation, and then we'll evaluate out of sample performance on the test data set using various quantitative measures and also with visualization. To summarize this video, we discussed the problem statement that will be implemented through R programming. In this video, we'll start with our implementation of ABC case study regression problem. We'll start with the ABC case study problem. We'll conduct the following steps. First, we'll load the relevant packages. In this case study, we are going to use read Excel package. This package will help us in reading Excel files, data in the Excel format. We'll make use of lubridate package, which will help us in date time manipulation. Then we'll use moments package for understanding various properties of data. Then we will load car package along with LM test will help us in various regression related aspects. And lastly, we have sandwich package that will help us in handling the estimation related issues in the regression. So with this, now we have loaded all the relevant packages. As a next step, we'll set our working directory. Please remember it is always a best practice to set the working directory. In order to set the working directory, we'll go to this session button, set working directory, go choose working directory. We have this particular file and folder. If I put on open button, notice a command appears on my console window. This command suggests that now that this command is run, appropriate working directory has been set. So for reference, I'll just copy paste this command on my code. So now that my working directory has been set, I can read the data file. So data, I will use read Excel command. The file name is abc.xlx. You can save it with any name. I have the file in with the name of abc.xlx. So now the file is saved. You can check a few initial elements of the data file by using head data command. Notice there's a date variable, there's a price variable, a return variable abc, sensex returns, dividend announcement dummy variable 01s, sentiment variable, and nifty, as we have discussed during the case study problem statement discussion. You can also check the dimensions of this data with this dim data command. It has 5,153 rows, that means 5,153 daily observations for 7 variables that we just saw. One important issue to be noted, you can check the class of various elements. For example, if I want to check the class of date variable, let's see. So I put dollar symbol, which means I am accessing that variable inside data frame. So it's already a date variable. Also, please note there is a time element, which is a spurious kind of spurious in nature. we need not handle this time element for now. We only need date, which means month, day, year. So I want to remove this particular aspect. I can do that very easily. I can simply just run this date, data, $date, and I can change the convert type to date. Earlier it was in POSIX-CT type of class, which includes not only date but time element. Since we are making use of only date element, I'll simply convert it to the date part. So now if I run this, notice the time element is eliminated, only date is there. I can run this class command again, so its class is date. So now it's not anymore the POSIX-CT element that it was earlier. Now it's only purely a date element. So to summarize this video, we set the working directory, we load the relevant packages, and then we set the working directory. We read the data file, which is abc.lx, in our data variable, which is essentially a data frame. We can check that also. For example, you can type the class command and check the data frame. It's a data frame. Then we check the dimensions of this data. We converted our date variable from POSIX-CT datetime object to purely a date object. From the next video, we'll try to visualize the data with its relevant properties. In this video, we'll conduct the visualization of data. We'll visualize the data. We'll examine key variables. We'll conduct the visualization of key variables, including returns on ABC and the market variable, that is Nifty. So first let us plot the ABC returns. So we'll use the plot command. On the x-axis we'll have the date variable. On the y-axis we have the return variable. We'll give the x-axis name using xlab command as date. So this will give us the x-axis as date, and then y-axis label as, we'll keep the y-axis label empty, but we'll give them central heading. We'll use central heading or main heading as ABC returns. So we'll plot the ABC returns along with prices, and we would like to see the plotting format in the line form. So we'll put type as L. Now as soon as I run this command, we'll notice that a plot will appear on the plot window here. We can zoom it. You can see the plot. You can see there are some extreme falls here around 2005 and 2008 and 10. Extreme down movements, increase in volatility. If you want, you can export this plot to save as image. You can use different image formats to save this plot. For example, you have PNG, you have JPEG, TIFF, various formats available to save. Also, you can export it in the form of PDF. You can save it as PDF, or you can copy it to clipboard and then paste it on Word document and PowerPoint presentation and so on. So this is the return variable, ABC returns. Next, I would like to plot the cumulative returns on ABC. So how to compute cumulative returns? Let's name this variable as CUMRET. So we would like to plot this cumulative return variable. The simple way to compute cumulative returns are use data $price. This will use the price and divide it by the beginning price, opening price. So any price divided by its opening value will give us the cumulative returns here. So I need to use the first value of price, and then I subtract it from 1 to reflect the return aspect. So this will compute the cumulative return in my data cumulative return variable. Now I need to simply plot it. So I can use the plot. Again, I can simply copy paste the command that I used earlier, the same command, only that now instead of writing as ABC, I can use this new variable CUMRET, cumulative return variable. I can use that and then name the plot as cumulative returns. And if I run this, the cumulative returns, you can see the cumulative returns provided here. So it looks like this. There is a sharp fall around here, 2005. These are cumulative returns. Now we'll plot the market returns. So we'll plot the Nifty returns. market or Nifty returns. Very simple. I don't have to do any extensive coding for that. I'll simply use my plot command that I wrote earlier, and instead of using ABC, I will do a minor change here. I'll write Nifty, so this will give me the market return. Nifty, other things remaining the same. I'll use the, instead of ABC, I'll change the central heading to market returns. And now if I run this command, notice these are my market returns. So these are simple market returns. Next we'll plot the cumulative market returns. Cumulative market returns. I have to just write a very simple command, which is data dollar cumulative. This time around we are computing Nifty cumulative, so I'll use this, and a very simple sum command, cumulative sum command, to compute the cumulative Nifty returns. This will provide me with the cumulative Nifty returns, and I will not write the command again, so I'll just simply use the same command that I used earlier, and I'll just change here cumulative return. Instead of cumulative return, I'll use cumulative Nifty returns, and in the central heading I'll change the name to cumulative market returns. So here I can see the behavior of cumulative market returns easily. This is the behavior of cumulative market returns. To summarize this video, in this video we conducted basic visualization of return variables. This included ABC returns and Nifty returns. We also plotted the cumulative returns. In the next video, we'll conduct the summarization of data. We'll provide some summary measures. We'll also have a look at the normality, skewness and kurtosis of the data, and stationarity of the data as well. In this video, we'll discuss the basic properties of our data. We'll start with a very basic summary measure. So we'll start by summarizing the data. For that we'll use summary command, simply summary command. And for summary command for ABC returns, we can see how ABC returns are distributed. The minimum value, which is quite high, and the maximum value, and first quantile, which is 25%, median value, which segregates the data between two halves, then mean of the distribution, and 75 percentile of the data. So these values are provided. Similarly, I can examine the summary of Nifty market index, which is this. So here also we can see extreme return, which is -14%, maximum is around 15.97, which is 16%, and same matrix, that is first quantile, median, mean, and third quantile. In the next step, we'll conduct a very important operation. We'll try to see the probability density of our data. In R, the same can be implemented with this plot command, and then density data dollar ABC. So this will plot the simply the density of ABC, but we want some aesthetic aspects also. So we'll type main as we'll type here as density. This is a density graph. So we'll type density graph, and then we'll name the X and Y axis. So X axis will just name simply the data. Also, we would like to, since we are plotting the density for both market and ABC, we will try to give them different colors. First, we'll plot the density of stock ABC return density in red. Let's give the line width of 2, so it will plot a slightly more solid line. Line type as 1, so a more solid line will be there. And we probably will, if you do not specify, the limits can be extremely large, so we'll restrict the limits of x-axis to -0.6 to 0.6. Although these will change depending upon your final result. You may modify and tinker with that a little bit here and there to improve the aesthetics. Next, with this lines command, I do not want to plot a new graph. On the same graph, I want to plot Nifty return, so I'm using lines command, Nifty. Then I would like to specify the color. Earlier I have used the red color to plot the ABC return, so I'm using the blue color to plot the Nifty returns. And line width, again I'll use the line width of 2. So this will be plotting the density of Nifty, and then I would like to add a nice legend on one side. So in order to check this, first let me plot the, okay, so this is my plot of ABC return, then my density plot. In blue we have Nifty. So now there's some empty space on probably the top left, so I'll use that space to put my legend here. So top left, and I'll use C, ABC. Then I'll name the next legend as Nifty because of this sequence. Since ABC is in red, so I'll use the red here, and Nifty is in blue, so I'll use the blue here. And now I'll run the legend. So if I run this legend, a very nice legend will be added. So use fill equal to color, and now the legend is added. Let us enlarge this plot a little bit. So notice on this plot ABC is plotted in left, and notice the behavior of ABC. It is extremely left skewed. You can see the extreme left tail of ABC, while Nifty is rather more balanced and symmetric in blue. Nifty returns are more symmetric over the sample period, while ABC, which is in red, are extremely skewed towards the left. That means there are extreme negative returns, which we also saw in the summary measure. So it is sort of confirmation of that. To summarize this video, we first summarized the Nifty and ABC returns using summary command, and then we plotted their density distribution to understand the basic characteristics of our return data for ABC stock and Nifty. In this video, we'll examine the normality and stationarity of the data. Now, first, as a part of normality examination, we'll start with the skewness of the data. We'll write skewness data dollar here. So we'll compute the skewness, which is very high negative, as we already saw in the diagram. The skewness of ABC is extremely left skewed. Then we'll examine the skewness of Nifty returns. So the Nifty is also negatively skewed, but the skew is not very high. But we want a slightly more solid evidence for that. So we'll conduct basic Agostino test of skewness. So we'll type data dollar ABC, and this will provide a more statistical measure. And notice that it provides you with a p-value which suggests that the skewness is statistically significant, in fact very significant, for ABC returns. Similarly, we can compute the skewness of Nifty returns. So here we computed the skewness of Nifty returns. This is also in terms of magnitude not very high, minus 0.177, but its significance is quite high. So this is also slightly negatively skewed and low in terms of magnitude, but reasonably higher in terms of statistical significance. Now, skewness is a measure of asymmetry on the left side or right side. In the remaining part, we'll discuss the kurtosis measure. So we also examine kurtosis measure. Kurtosis is a measure of peakness and tail. So how peaked or less peaked as compared to normal distribution, and how tailed it is, whether tails are fat or not. So first we'll compute the kurtosis of ABC returns. The kurtosis is quite high. We'll also measure the kurtosis of, probably this can be accounted to the extremely fat tails of ABC and the peak nature, as we saw in the density distribution. Nifty also has a very high kurtosis, so we can see that it also has a very high kurtosis. Normal distribution has a kurtosis of 3. So as compared to normal distribution, the kurtosis levels are very high. Now we would like to again have a slightly more statistically significant evidence, so we'll use the Anscombe test. First we'll compute it for ABC returns, dollar $ABC. For ABC, okay, so the kurtosis is not equal to, in fact very significantly different from 3 for ABC, which we expected. We'll also see the kurtosis. Kurtosis is the measure of peakness and tail, how fat tails are or how peaked the distribution is as compared to normal distribution. So the tails are fat and the peakness is very different from normal distribution. Here also kurtosis is very significantly different from normal distribution. As a final test, we already know although that skewness and kurtosis are very different, and as a combination skewness and kurtosis decide whether data is similar to a normal distribution, the bell-shaped curve that we discussed. As a final test, we would like to have Jarque-Bera test, or it's called Jarque-Bera test or Jarque test, which will give us a sense of its normality, although we already know that data is not normal, but it's still a combined measure of normality, which is very high, which is much greater. So data is non-normal. As you can see, this is a combination of extreme skewness and peak nature of ABC. Although in case of Nifty, the skewed nature was less. It was not as skewed, but still as compared to normal distribution, it was skewed. And the tails were fatter on both sides as compared to normal distribution. Same for Nifty as well. Nifty, we can see it was symmetric, but still it's non-normal. Now normality is high. We'll see while working with the regression model, we'll see how to deal with these issues. But we have seen the summary measures. Now just to summarize this video, we computed the skewness, kurtosis and normality of the data, overall normality of the data. We found that ABC was extremely left skewed, and both of the distributions have fat tail as compared to normal distribution and higher peaks. This was statistically examined using Agostino's test and Anscombe test, and using Jarque-Bera test we also examined the overall normality of the data. We found that both the series ABC return series and Nifty return series are non-normal in nature, and the result is statistically significant as well. In this video we'll discuss a very important property, that is stationarity of the data. Stationarity of the data refers to the fact that the mean and standard deviation or variance, as we have already discussed the concepts, these are changing with time, and if these parameters such as mean and variance are changing with time, estimation is fraught with various econometric issues. So before estimating any kind of relationship, it is important to know whether your data is stationary or not. There are three very useful tests for that, and these are augmented decay Fuller test, Phillips-Perron test and KPSS test. For these tests we need to load a very important package, which is URCA, unit root test. So we'll load this package URCA, and now we'll start with our, first we'll conduct the augmented decay Fuller, or often called ADF test. The command is quite simple. We'll write summary and ur.df for augmented decay Fuller, df data dollar ABC is our price series. So we'll use ABC, and notice the null hypothesis of this particular augmented decay Fuller test is that data is non-stationary. Since notice the test statistic, it is minus 51.7, which is much lower and much higher in terms of magnitude as compared to 1%, 5% and 10%. Therefore, with a lot of confidence we reject the null and we say that data is stationary. Please note, this is a non-stationarity test. That means null hypothesis of this is that data is non-stationary. Very similar syntax we'll use to check the stationarity of the Nifty returns. If the returns were non-stationary, any model such as regression algorithm will be difficult to estimate properly. So we'll check the Nifty returns also. Nifty returns also, notice that we reject the null of non-stationarity with a lot of confidence. So again the data is stationary. But while testing stationarity, it is very useful to test through a number of tests. So for example, augmented decay Fuller tests were tests of non-stationarity. Here we'll be using tests such as PP test also. Look at the test such as ur.pp, and notice here again this is also a test of non-stationarity and we reject. Notice the test statistic, which is very large in magnitude, very negative as compared to the standard statistic. Given the large test statistic, we can reject the null and again say that data is stationary. So here also the null was of stationarity, so we reject the null and we say that data is stationary. It is very high tested statistic, so we are again and again saying that data is stationary. Another very interesting test, and generally it is required to test through stationarity test also. So earlier, both the tests earlier that we did, Phillips-Perron, augmented decay Fuller, they were test of non-stationarity. Now we'll make use of KPSS test, which is the test of stationarity. So first we'll run the KPSS for ABC returns, and notice the test statistic is much lower than 1%, 5% and 10% level. So data is, again, we are not able to reject the null of stationarity, so data is stationarity. Similar test we conduct for nifty returns also, KPSS test, and here also we find the data is stationary. So we have conducted the stationarity test. To summarize this video, we conducted test of stationarity and non-stationarity. Here augmented Dickey-Fuller and Phillips-Perron tests were tests of non-stationarity, where null hypothesis was of non-stationarity and rejection of null indicated stationarity, while KPSS test was of stationarity, and we failure to reject the null, we failed to reject the null, which indicated again the stationarity of the data. In the next set of videos, we'll start with training and testing of regression algorithm and prediction of stock returns. In this video, we'll segregate our main data, which is ABC stock return data, into training and test data. Training data will be employed to train the linear regression algorithm, while test data is employed to test the out of sample forecasting efficiency of the algorithm. So we'll start the analysis by segregating the data into training and test data. As a first step, we'll create our train data segment, which is equal to main data, and we'll tell R that the date should be less than equal to. Now we'll filter the date with 2017, less than 2017, December. So 1st December 2017 is our cutoff point, and this is the maximum, and it should be great. Let's say we also filter observations before 2006. So let's say we also do not want to go too early, so we filter those observations that are for which the year is greater than 2006. So we are filtering from 2007 to almost 2017. We are filtering all the observations. So this is our train data, and let's check this. So we'll check the head of train data, head of train that starts from 2007, as we can see here. Let's check the tail of the train data. It ends with 2017. As we can see here in the date segment, we can see on the console window it ends with 2017. And if you look at the dimension of the train data, it has 2850 observations. Similarly, we'll select our test data. Our test data is again in a similar manner. We'll filter it. Data $date should be greater than, and now this time around we'll use the exact same date criteria, which is greater than as dot date, and we'll precisely select the date that we selected earlier. We'll select the same date, in fact. So all the observations with higher date number will be taken here. So now this test data will contain the remaining observations that are above 1st of December 2017. Let's examine this. So the head of the test data starts from 2017, in fact 4th of December, and look at the probably 2nd and 3rd are holidays. And if you look at the tail of this, tail of the test data, the tail, it ends with 2019. And if I examine the dimension of test data, so around 478 observations to test the algorithm. So to summarize, in this video we segregated our data into two segments. First, the training data, which starts from year 2007 and ends at 1st of December 2017, while the test data contains the remaining observations starting from 4th of December 2017 up till 2nd of October 2019. In this video, we'll train our simple linear regression model by regressing the ABC returns on nifty returns. So we'll model simple linear regression model by examining the ABC returns and Nifty returns relationship. So in R, this relationship examination is done with a very simple LM command. So we'll run this LM command, which indicates some kind of linear regression model is about to take place, and where we are regressing ABC returns. Here this notation suggests that ABC is the dependent return variable, ABC returns, and the independent variable is Nifty. Our data is train data we are using to train this linear regression model, and the output of this linear regression model, the train model output, the coefficients will be stored in SLR object, simple linear regression. Let us see the summary of this object. We'll assign the summary to the model object, summary SLR. Let's have a look at this summary variable. I can simply extract this by printing model. Notice the console window. On the console, we can see the printed output. In the output, the following objects to be noted. First, note the coefficient of Nifty, which is 0.397. This is also the measure of beta that we have discussed. Recall the discussion on beta, that beta represents the sensitivity of ABC returns here. That means if market moves by 1%, ABC stock returns move by 0.39%. Also notice the t-value of the coefficient, which is heavily significant. Remember, this t-value is computed as the ratio between estimate, which is the coefficient, that is 0.397 here, divided by the standard error. Now, this t-value 18.67 is very significant. The 3 stars suggest that it is even significant at 1% level. Recall our discussion on the significance levels. Null hypothesis here is that this coefficient Nifty has a value of 0, which means Nifty does not affect the movement in Nifty do not affect the returns of ABC stock. However, given this result, the very high significance of this result at 1%, we can say definitely there is a positive impact of Nifty, that is market movement, on ABC returns. Here it appears if market moves by 1%, ABC stock moves by 0.39%. And this relationship is statistically significant at 1% level. So we are very confident. In fact, we are more than 99% confident that there is a relationship between Nifty returns and ABC stock returns. Moreover, notice this adjusted R square here and the multiple R square. In fact, we'll focus on adjusted R square, which is a more improved version. It is 10.87%. This suggests that out of the total variation in ABC return, 10.87 variation is explained by Nifty, which means, and recall our discussion on the market risk and systematic risk, that almost 10.87% part of the overall risk, total risk, if total risk is 100%, 10.87% part of the risk is market risk or systematic risk driven by the market movements. In this case, market is proxied here by Nifty. The remaining approximately 89.21%, around 89%, is the idiosyncratic risk, which is specific to ABC stock. The remaining 10.87% is driven by market and explained by market. So this is our interpretation of the overall regression. To summarize this video, we examined the relationship between ABC returns and Nifty returns by regressing ABC returns on Nifty returns. We also examined the output of this regression model. We discussed the coefficient, its significance, the idiosyncratic and systematic part of the risk associated with ABC stock return, and we have now trained our linear regression algorithm. In fact, this is a simple linear regression algorithm because we are using only one variable, which is Nifty. So now that we have trained our simple linear regression algorithm on the training data set, now we will examine the efficiency of this model in subsequent videos. We'll examine some of the econometric issues that this model may face and how to deal with them. In this video, we start with the residual diagnostics of the model. Residual diagnostics. First, we'll look at the density plot of the error terms. So we'll use density plot. Recall that we have already stored our trained model in the model variable or model object. So we'll simply use the model residuals. So we'll plot the density of this. Let's examine the density plot of residuals. Notice that while the shape of this density is relatively similar to normal distribution, however, its left tail is extremely long, which suggests that it is extremely skewed. We can also corroborate this by plotting the density plot of studentized residuals. For that, the command is simple. We can just write the same density plot and we type R student. But this time we'll pass on the original model as LSR object, which is the model object that we created. So again, it is also very similar. So the density plot of residuals and as well as studentized residuals is extremely left skewed. Students distribution is essentially t distribution. So these are standardized errors. And as we can see, it is extremely left skewed. Another test to examine the behavior of the model and its residual is QQ plot, which checks the normality. Let's examine the QQ plot. So we pass on the fitted object SLR, which we already fitted. We also would like to know some of the extreme observations that may create problems for us. So we'll give the number as n equal to 10. So this will identify 10 extreme observations for us. Let's see. So we'll run the QQ plot command. Also, we would like to see some of the extreme observations. So I'll type id equal to list n equal to 10. So we would like to highlight 10 extreme observations. I run this command and the model is plotted here. So we can see the quantile wise distribution of studentized residuals. So the residuals are plotted and we can see this number of observations that are extreme. Observation number 72, 152 and 2544. These are some of the extreme observations that depart from the normality. These on the fitted model, these observations are plotted along the fitted model. We can see the observation numbers. The studentized residuals are plotted here. We can see some of the observations plotted here. So this is, and we can see that most of the time the observations, the residuals are along the normal line. The straight line indicates the normal line. The observations that deviate from the straight line indicate deviations from normality. And we can see some of the fitted observations on the extreme left and right end. These some observations deviate from the normal distribution. Normal distribution here is represented by the straight blue line. Lastly, we can also conduct the outlier test. Now, there is a basic outlier test and it will also adjust for Bonferroni values, adjusted p-values. Let's see them. So if I run this, notice unadjusted p, there are a lot of very significant unadjusted p-values, but once there is Bonferroni correction, one can see the significance is less, but still we have there are 6 extreme values and these appear to be very similar to the earlier ones. So these are our extreme values. If you want to know more about these functions and their theoretical underpinnings, you can simply type question mark QQ plot and see the background, the entire background of these commands. For example, this is for quantile comparison plot to check the normality, and the outlier test also. You can check that. The theory behind these commands by running the question mark. You can read more and more about these commands. Lastly, if you feel that these observations are vitiating, these extreme observations are vitiating your estimation model, you can remove them from their model. You already have the observation numbers. You can remove them from the model and then run the model again to improve its estimates. To summarize this video, we created density plot of residuals. We also have examined the studentized residuals on the density plot. Next, we checked the deviations from normality with the help of QQ plot. And we also conducted the outlier test to see some of the outlier observations. We found that there are a number of outlier observations that may vitiate the estimation. As a future course of action, one can remove these observations from the model, but please note, sometimes these extreme observations also carry useful information. probably that may help us model extreme values representing extreme events. So sometimes it is not advisable to remove these values. So a subjective judgment call may have to be taken here.